OCI session, and today we're going to be covering exam 1 content specifically for Jeske's class. Alexia and I have both taken organic chemistry and have done well, so we feel like we have some information to give you guys and help succeed in organic chemistry. All right. So here, we're going to do a quick attendance. If you can scan the QR code and fill out the poll. This exam, from what I heard from Jeske, is going to cover 7 main topics: some Gen Chem review, functional groups, resonance, acid-base chemistry, nomenclature, Newman projections, and chair conformers. Yeah, so let's get started. So this is going to be our first part, Gen Chem review. Valence electrons and formal charges, very important. Not right now, but later on in resonance, you'll use this. Valence electrons are the electrons around the atom's outermost shell. And these are the electrons that you're going to mainly use when drawing air pushing mechanisms in resonance or acid-base chemistry. And for the valence electrons, it's most stable. The atom is most stable when it has 8 valence electrons or full octet, which is what this octet rule states. And there are a couple exceptions like hydrogen, which in this case can only hold 2 electrons, and then sulfur as well. And based on how many electrons they have, valence electrons, they can either gain or lose electrons, which is why when you see atoms in a molecule, they can have charges. They can have negative or positive charges. And that negative and positive charge can be represented as a formal charge. And formal charge is just a number to show you, how many electrons there are, valence electrons, or how electron deficient they are. And to calculate this, there's a general formula you follow, which is number of valence electrons minus number of lone pairs minus number of bonds. It's a pretty straightforward formula. You might not understand right now, but if you do a couple practice problems, it'll be easy. All right. Any questions regarding the content on this slide? Yep.
Related to the first slide,
Yeah, for sure. This QR code? Yeah. Oh, sorry.
Slides.
It doesn't matter how you downloaded it. Okay. So let's dive straight into some practice with formal charges. I'll do the first 2 examples with you guys, and then I want you guys to do the 3 on your own. All right. So if we look here, we're trying to assign charges to atoms that have electrons or that are electron deficient. And if we look here on this carbon atom here, this carbon atom has 1, 2, 3 bonds, right? And normally carbon has 4 valence electrons if you look on the periodic table. So if you use a formula, the formal charge, I'll abbreviate with FC, equals 4 valence electrons minus the lone pairs, which in this case there are none. So 0 minus the number of single bonds, right? As stated right here, number of bonds. And we have 1, 2, 3 bonds. So 3 bonds. And that'll give us a positive formal charge. So the formal charge on this carbon would be a positive 1. And you don't need to write out the 1. It's assumed that if you write a positive or a negative charge, there's a 1 next to it. Okay. And also, quick note, when you do negative signs in formal charges, make sure to put a circle around it because it may be assumed by the grader that it's a bond and not actually a negative formal charge. So make sure to always circle your charges. All right, that's the formal charge on that carbon. Let's move on. If we look at this nitrogen, this oxygen here, this oxygen normally has a valence electron of 6, but we have two lone pairs. I mean, one lone pair, which means two electrons. So two electrons minus the number of single bonds, which is two. Wait, how do we do this? It's like three bonds, sorry. So that would be positive one. So you would indicate that again as a plus charge here. Does that make sense? Okay. Well, let's cover some other ones as well on this molecule. For example, this carbon. This carbon has 4 valence electrons minus, there's no lone pairs on these, so 0 lone pairs. And then the number of bonds, we have 1, 2, 3, 4, 4. So that would be a formal charge of 0. That's why we don't put any charges on there, no positive or no negative sign. And that's going to be the same case for every single molecule, every single atom besides these two. Let's move on to the next one. If we look here on this carbon usually has 4 valence electrons minus no lone pairs, so 0 electrons, minus the number of bonds, which is 3, 1, 2, 3, which gives you a positive +1 charge. So this would be positive charge or a carbocation. Let's look at this oxygen right here. This oxygen usually has 6 valence electrons. You're taking away the amount of lone pairs, which in this case, there's 3 lone pairs. So 3 times 2, 6 electrons, minus the number of bonds. And in this case, there's only 1 bond. So you take 1 bond away, and then you get -1. So that means that oxygen has a -1 formal charge, which you indicate by a negative sign. Does my thought process make sense to everybody? Okay. If we don't have any questions, then I want you guys to do the next 3 on your own. And we'll walk around to help you guys if you need. Go through these examples. Does anyone want to answer the third structure and tell us if there's any formal charges on any atoms? The nitrogen has a positive charge. That is correct because you got nitrogen usually has 5, and then you'd have 0 lone pairs minus 4 bonds, which is plus. So yes, that's correct. Is there any other charges on any other atom? Yes. You go through the same calculations and you'll get a positive charge. So yeah, that's all the formal charges on this molecule. What about the next one? If anyone, you guys got to that. The nitrogen has a negative charge. You're correct. You do the same formula, plug in the same numbers, and you'll get negative. Yeah, the oxygen also has a negative charge. What about this last one? Slack structure. You're talking about this one, right? Yep. What about this boron over here? What do you guys think?
You said negative charge?
Yep. Boron would have a negative charge because boron usually has 3 valence electrons. And there's 2 bonds right here, right? 1 bond here and 1 bond that's formed between the boron and the hydrogen. So that's 2. And then the number of lone pairs is 1 lone pair on boron. So 2 electrons. And then you get -1. That's why there's a negative formal charge on boron. Anything else? Yep. Same case here. Boron, bromine would have a positive charge. So let's move on. Formal charge is pretty simple. All right, bonds and electronegativities. Important thing on this slide is being able to identify whether a molecule is polar or not. And you're able to do this by comparing electronegativities of two atoms. So usually, so what electronegativity is, atom's affinity towards electrons. It wants more electrons if it's higher affinity. And that trend usually follows as such. You go from the bottom left of the periodic table to the top right. The more top right it is, the more electronegative it is. So in this example right here to the right, chlorine, we're comparing chlorine and carbon. And that shows the net dipole moment between chlorine and carbon. And same thing here. And to indicate the net dipole of this entire molecule, you just combine both dipole moments and show a general direction of where that's going, which is this right here. And if you have a net dipole on a molecule, that means it's usually going to be polar. So this molecule right here is polar. But just because you have a dipole moment in a molecule does not mean it's always going to be a polar molecule. And you can see this in the next example. In this example, you have dipole moments here, as discussed before, but there's also another one like this. And these dipole moments are on the exact opposite ends, so they sort of cancel out each other, which is why there isn't any actual net dipole, making this a non-polar molecule.
Typically, if the bond is not a carbon-hydrogen bond, it's going to be polar.
Yeah. And these values right here, it's just standard numbers, but you don't need to memorize any of these. All right. Just know the relationship between electronegativity. Okay. So let's do some problems. We're going to look at some of these problems and determine if the molecule over a molecule is polar or not. If we look at this first example, HBr, we're comparing hydrogen and bromine. Obviously, bromine is going to be more electronegative. So it's going to want to hog more electrons towards it, which is why you have this arrow to indicate that. And by drawing this arrow, you're basically drawing the net dipole as well. So since there is a net dipole, that means it's going to be a polar molecule. Let's look at the next one, CO2, carbon dioxide. Carbon and oxygen. Oxygen is more electronegative than carbon, so you'd have a dipole moment here. But there's also another oxygen on the other end, so you'd draw this here. And since these dipole moments are on the exact opposite spectrum, they're going to cancel out and have no net dipole, making this non-polar. Yep, this one is going to be polar actually. And take note that this oxygen here is going to have two lone pairs as well. And there's a net dipole like this.
So that just like makes it even more negative.
Yeah. What about D? Non-polar? Yep. These all have the same dipole moments, and since they're all going in the opposite directions, everything's going to cancel out. So it's non-polar. Pretty simple stuff. Okay. This is talking about boiling point. I think Jesky likes to give some of these type of problems, giving you guys multiple molecules and deciding which one has the highest boiling point. And with boiling point, you want to look at the intermolecular forces, and whichever one has the highest intermolecular force means that it's the most strongest. It has the strongest bonds, right? So it's going to be harder to break those bonds, meaning you're going to have a higher boiling point. So let's look at these two examples here. The oxygen on this molecule here can form hydrogen bonds, right? Hydrogen bonds form between nitrogen, oxygen, and fluorine. And since hydrogen bonds is stronger than van der Waals, which is the only thing that exists in this molecule, that means the IMF is going to be stronger in this molecule right here. And because of that, the higher boiling point would also belong to this molecule. All right. Given that, why don't you guys try the next one? What do you guys think? The one on the left? Yep. So these ones, they both have the same forces. It's just van der Waals, but this carbon, there's more carbons on here, right? So it's going to have more van der Waals forces, meaning stronger bond, higher boiling point. All right. In organic chemistry, you're typically going to see variations in how structures are drawn. And there's 4 different main type of structures. Lewis structures, which I'm pretty sure you guys are all familiar with. This Kekulé structure, which I've never heard of, but it's there. And we got condensed structures where you just write the formula out, but in individual atom components. And then the skeletal structure, which you guys are probably going to use the most throughout the rest of organic chemistry. This shows this is basically a Lewis structure without any of the carbon atoms or the hydrogen atoms shown. With also, it doesn't show any of the lone pairs. It just shows the charges. And when you look at a skeletal structure, it's assumed that you know there's a carbon there or a hydrogen there. Another important point about skeletal structures, we're going to use dashes and lines. Sorry, dashes, wedges, and lines. Lines are these, and these are on a plane. They're just flat. Dashes are ones that come out towards you when you're looking at it from the side. And these wedges are the ones that come out towards you. Dashes are the ones that go away from you. All right. And based on this skeletal structure, I want you guys to be able to determine whether they're identical, different, or constitutional isomers. I know Jesky likes to ask these type of questions as well.
I'm gonna define what each of them are real quick.
Oh, what?
Define what they are real quick.
All right. Identical means that, the molecules have the exact same configuration, same exact molecular formula. Different means it has a different formula and a different structure. Constitutional isomer means that it has the same molecular formula, but it's arranged differently. They have a different molecular representation, is what I'm saying. This one has more carbons, so this is different.
These are identical. This all should be right there.
Yeah, so that's constitutional. And the second one's different. Anyone got an answer for the first one? The first question, does anyone have a guess? Identical? Why do you think it's identical? They do have the same parent chain in that they both have a pentane group. But if you see here, the methyl's are in different places. In this one right here, the methyl is on carbon 2 and carbon 4, whereas this one, there's the methyl is on carbon 2 and carbon 3. And since it's not the same molecular representation, that means it's going to be a constitutional isomer because it has the same molecular formula, but different molecular representation. Does that clear up why it's not identical and rather a constitutional isomer? Okay. Anyone got a guess for the second one?
Different.
Yeah, they're different because you can just count up the carbons. This one, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the molecular formula isn't even the same, meaning that they're going to be a different molecule. Doesn't matter how it's arranged, they're going to be different. This is also another thing that I think Jesky likes to ask is he's going to give you one of these Lewis structures and he wants you to convert it into a skeletal structure, meaning a structure without any of the carbons or hydrogen showing. So give this a try. Seems like many of you have gotten it or are close to finishing. So let's draw this. So what I see is that this carbon here is bonded to a hydroxyl group and a carbonyl group, meaning it's going to be a carboxylic acid. So draw it like that. And then this carbon chain keeps on expanding. There's another carboxylic acid towards the end. And then there's a carbonyl group in the middle. And then there's this lone methyl group. So is that what you guys got? All right. You know, constitutional isomers, there's going to be many of them. There's going to be 6 to be exact for this one. I'll just show you like one of them. Essentially, what you can do to draw constitutional isomers is just move like some of these bonds around. So for example, you can draw something like this. And this would be a valid constitutional isomer because it has the same molecular formula, but a different molecular representation. All right. Let's move on. Molecular geometry. There's a couple you guys are going to have to memorize, which I think you guys probably memorized at this point, but if there's 2 electron domains, you can get linear. If there's 3 electron domains, you can get trigonal, planar, or bent. If there's 4, you can get a tetrahedral, a trigonal, pyramidal, or a bent structure. And this all depends on the number of single bonds and the lone pairs. So quick review. Let's try to draw the geometry of this, and then you don't need to actually identify the angles because that's not going to be tested at all, but try to give the Vesper name of the molecular geometry. So for this first one, we can see it's a CH4. And we can just draw it like this. And since it has 4 electron domains, no lone pairs, that means it's going to be a tetrahedral. And that's what I want you guys to do for the next 2. One. So CO2, I showed you the structure before, but the Lewis structure looks like this. Oops. And we can see that it's totally flat. It's a linear structure. So it's linear. BF3, 3 valence electrons, it can form 3 bonds. So B, F, oops. That means it has no lone pairs, so it's going to be a trigonal planar. Any questions? Nope. All right. All right, next topic is hybridization and bonds. Hybridization falls really well into resonance. Hybridization basically shows you the amount of electron domains there are. And electron domains is basically how many bonds you can form. And since every atom can form 4 bonds, you're going to have 1 s orbital and 3 p orbitals. And hybrid orbitals, as the name sounds, is when these orbitals form hybrids. They combine together. They have some percent of S character and some percent of P character. So you can have an sp2 in which you'd have three sp2 molecules, three orbitals, and one unhybridized p orbital. If we take sp, for example, you'd have an sp, and two unhybridized p orbitals. If we take sp3, for example, all of these will be hybridized. Like that. Does that make sense? Just shows you how many electron domains there are. All right. So for this one, it's asking you to identify how many sigma pi bonds there are, and then identify any molecules that are, identify how many sp molecules there are. So for the first one, I'll walk you through. We can see sigma bonds are usually just single bonds, and then pi bonds are double bonds or triple bonds. So all we got to do for the sigma part is to look for any single bonds. That means any bonds that are forming hydrogens, like the carbon and the hydrogen are forming bonds, even though it's not shown. So in this example, this carbon here, although it's not shown, is bonded to three hydrogens. There's a hydrogen bond right here as well. And then there's three hydrogen bonds on each of these methyl groups. So now all you got to do is just count how many single bonds there are. If we see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 3 on each of these. So 13 plus 3 times 3, which equals 22 sigma bonds. That's how you count how many sigma bonds there are. And then pi bonds, like I said, are going to be double bonds or triple bonds. And in this case, let me actually erase all this. We have 1 and 2 pi bonds. Next is asking you how many sp orbitals there are. And sp orbitals, we have, hold up. We don't have any sp because there's no bond. That's only 2 molecules each. Because this is, yeah, so there's 0 sp. sp2 is going to form 3 bonds. So we have this molecule right here, since it's forming 1, 2, 3 bonds. And then, what else? Is there anything else? And then this one right here, actually, because there's 1 hydrogen bond here. And then there's another one here and then another one here. So that's another sp2. And then this one would also be an sp2 because there's a hydrogen right here. So there's 1, 2, 3 bonds. So there's 3 sp2 molecules. And then to identify sp3s, it's basically got to have 4 bonds. So this carbon right here, it has 4 bonds because it has forming 3 bonds with the hydrogens, 1, 2, 3. And then another bond right here. Since it has 4 bonds, it's going to, yeah.
I think it is.
You're correct, actually. That would be sp2. So the answer key is wrong. Yeah. So this would have 3 electron domains since there's 1, 2, 3. Good catch, by the way. So that would also count as a sp2. So this would be 4. Back to sp3. It has to form 4 bonds. We got one right here. We got another one right here. We got another one right here. Another one right here. Another one right here. They're all forming 4 bonds. So they're all going to be sp3. So we have 1, 2, 3, 4, 5 sp3 molecules. Yeah. It'd be an sp2 because when we do hybridization, we're counting the electron domains. And if we see here, a lone pair is going to be one electron domain. There's another one right here, so that counts for two electron domains. And then another electron domain is this single bond right here. But there's also a double bond, right? And we told you guys that double bonds occupy pi orbitals. So that doesn't count. That would be in the unhybridized p orbital. So this lone pair would be in an sp2 orbital. This lone pair would be an sp2 orbital. And one of these double bonds is going to be in an sp2 orbital. And the double bond here is going to be in an unhybridized p orbital. That's why it's an sp2. Yes, you can write it like that as well. It'd be an sp2 plus p. I want you guys to give the next one a shot as well. Okay, we're going to do the second problem. And Alexi is going to show you a easy way to understand hybridization.
I'm teaching y'all the secret goated method. Like, y'all should use this way. All right, so a bond, a double bond, a triple bond, and a lone pair. Each of them is worth 1 point. 1 point, right? And then we're gonna write out S, P, P, P. And then we'll write 1 point, 2 points, 3 points, and 4 points. That's how you want to set it up when you're trying to find out hybridization. So first, we're going to look at this carbon right here. This carbon has 3 hydrogens, right? So we're going to count up the bonds and add up the points. So we have 1 point right here, 2 points, 3 points, and 4 points. We go back up to our SPPP. 4 points ends right here. So this carbon is sp3, right? On this next carbon here on the triple bond. Right there. 1 point for this single bond and another point for this triple bond. That's 2 points. So we go back up to our SPPP. That ends right here. So that's SP. Does that make sense? Same thing for this one. This one's also SP. So in total, we'll have 2 SPs. For this one, this has 2 hydrogens, right? We count up those bonds and add up the points. That makes 4 points. Up here, 4 points ends at sp3. So that's also sp3. Same thing for this one. This carbon right here attached to the oxygen. 1 point for the single bond, another point for the single bond, and a point for that double bond. That's 3 points. So we go up, that ends right here. So that's sp2. This oxygen, the lone pair, each are 1 point. So that's 2 points for those 2 lone pairs. And then the double bond, that's another point. So that's 3 points. That will make it sp2. These carbons right here, it has 3 bonds. Each of those bonds are 1 point. So it's going to end up as sp2. Same thing for these ones. This one, 1 point for each of the bonds. That's 3 points. sp2. This oxygen, 1 point for each lone pair and 1 point for the bonds. So that's sp2. Does that make sense? Thumbs up if y'all get it. Pretty simple.
Yeah. All right. So if you counted these all correctly, you'd have 24 sigma bonds, 6 pi bonds, 6. How many sp2s are there? There's 1, 2, 3, 4, 5, 6, 7, 8. 8. You'd have 8 sp2s, and then you'd have 3 sp3s. All right. Next, we're done with Gen Chem review. Functional groups, this is gonna be quick because this isn't something I'm gonna be able to teach you. It's just more so you guys have to memorize these. And to do that, we made you guys a Quizlet. That's you guys can quiz yourself on what these functional groups are. All right, everyone got the QR code, I'm assuming. So let's do some practice problems. Is asking you to draw the alcohol group, functional group. And alcohol functional groups look like this. It's a hydroxyl group. Just got to know that off the top of your head. Esters look like this. You have a carbonyl and then a adjacent oxygen right next to the carbonyl. And then amine looks like this. It's just if you took biology, this is essentially an amino group. Same thing here. So that's the answers. All right, let's move on to resonance. Resonance is probably one of the difficult topics on this exam. Resonance is the movement of delocalized electrons, meaning it's not localized and they're free to move. And you got to know the difference between delocalized and localized electrons. But to put it simply, resonance, you got to follow a couple rules. One of the rules being that since it's the movement of delocalized electrons, these delocalized electrons take form in double or triple bonds or lone pairs, and they shift through positions of overlapping p orbitals. So, oops. You're going to have a system that looks like this, basically. Two p orbitals overlapping together so that electrons can move along. So that's one of them. And since it's overlapping p orbitals that delocalized electrons can move through, only atoms that have p orbitals can participate in resonance. So this means that sp2 orbitals or sp orbitals can participate in resonance because they have an unhybridized p orbital. In the case of sp2, you have 3 sp2 orbitals and 1 unhybridized p orbital. In the case of sp orbitals, you have 1, 2, and 2 unhybridized p orbitals, which automatically means that if you look at sp3, all of the orbitals are hybridized. They're all sp3. So sp3 atoms cannot undergo resonance because they lack that p orbital overlap. And then the last rule, probably the most important rule with resonance, is whenever you draw your arrow pushing mechanisms for resonance, you start from a source of electrons, meaning areas of high electron density to lower areas of electron density. And high electron density can take form as double bonds, triple bonds, negative charges, or lone pairs, because these have a surplus of electrons. And what not to do is to draw resonance starting from positive charges, single bonds, or hydrogen atoms. Got them? So these are basic rules for resonance. Oh, this slide's messed up. All right, this slide's kind of messed up, but I'll explain through them. Yeah. All right. So for jet ski, all you're gonna need to know is these 5 resonance patterns: allylic lone pair, allylic carbocation, lone pair adjacent to carbocation, a pi bond between atoms of different electronegativity, and conjugated pi bond systems. Allylic lone pair is pretty simple. You're going to be working with a negative charge, meaning a surplus of electrons. So you start your arrow pushing mechanism from the electrons, bring it here, bring the double bond out, and make that a lone pair. Allylic carbocation is the exact opposite. Instead of a negative charge, you're going to be working with a carbocation or a positive charge. So in this case, the electron sufficient group would be this double bond right here. So you bring this and shift the charge to the other atom. Lone pair adjacent to carbocation. So this is a combination of the last two. You work with a negative and a positive charge. And since we always start from an area of high electron density, we start from this lone pair, bring it down, and make it into a double bond like this. Next one, pi bond between atoms of different electronegativity. So in this example here, you see that we have a carbon and an oxygen. Oxygen is more electronegative. So it's going to want to hog all of those electrons to itself. So to show that, you're going to use this arrow here and bring that double bond and make it into a lone pair. And then the last one is a conjugated pi bond system. You're basically going to move the double bond to the place where there wasn't a double bond, and the places there was a double bond, they're not going to have it anymore. And that's probably the simplest one, to be honest. And what it means by conjugated pi bonds is it's conjugated when you have a double bond and then it skips a double bond and then it forms another double bond like this. So this would be a conjugated system. All right. Now for each of these, because we learned the resonance patterns, I want you guys to determine if these resonance structures are valid or not. So if we look at the first one and start from this negative charge, even if we do resonance patterns like this, you're ultimately going to get this right here, which is not equivalent to this molecule. So this resonance structure is not valid. So it wouldn't have any resonance structure, so you put no. Same case for this, the next one. There's no resonance patterns you can do in this case, so this would automatically be a no. And then if we look here, this would also be the same case. Whatever resonance pattern you do, you're not going to get one of the other molecules. So this would be a no. This last one as well, you can't do any other patterns here. I mean, you can, but you're going to get different structures. You can do this and get this right here, but that's not equivalent to this structure. So there's no resonance patterns you can do. So all of these, the answers were no. All right, second practice with resonance. Based on what I told you guys, I want you to draw proper arrow pushing mechanisms for this resonance structure. Together, I see a lot of confused people. So whenever we do resonance, like I said, we're going to start from a source of electrons. So identify those source of electrons first. We can either start here, here, or this lone pair here. But these two right here can't participate in any resonance patterns that we learned. So we're going to start from the lone pair on the oxygen, the nitrogen. So what we can do first is we can bring this lone pair and do a allylic lone pair, which will get you something like this. And then from here, we can do another allylic lone pair. Take this lone pair here, make a double bond, and bring this double bond and make it into a lone pair. And those will be your resonance structures. You only have two. Ignore this arrow. Do these arrow pushing mechanisms make sense to everybody? Okay. Okay, we're going to do resonance hybrids now. Resonance hybrids is just a combination of every single resonance structure you can do and representing in one picture. And to do that, the only difference between a resonance hybrid and a resonance structure is instead of pi bonds, double bonds, making them a straight line, we're going to use dashed lines instead. And then wherever there was a full charge, you're going to use a partial charge, so the delta sign. And that's about it. And when you draw resonance hybrids, none of the lone pairs are shown. All right. Another topic for resonance is to be able to determine which of the resonance structures you drew is most significant. And you're just going to follow these three rules. The first thing you look for is if all the atoms have a filled octet. So if we see in this example here, every single atom here, except this carbon, has a full octet. Full octet means 8 electrons. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So that's a full octet. But this carbon is 1, 2, 3, 4, 5, 6. And it's missing 2 electrons. It's not a full octet. So that means this is going to be less significant than this structure right here. Because if we look here, everything has a full octet. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This carbon now also has 1, 2, 3, 4, 5, 6, 7, 8. Since this structure has a full octet, it'll be a more significant or more contributing resonance structure than this one. Next thing you look for is to look for the molecule that has less charges. So if we see here, this first molecule drawn here is the most significant because it has no formal charges, the least amount of charges, while the last two have 2 formal charges, right? A positive charge and a negative charge. But how to differentiate them, right? They both have the same charges. You can do that by going back to the first rule and identifying the number of filled octets. If we look here on this third structure, we see that this carbon is a carbocation. That means it's not a full octet. It only has 6 electrons around it. So this would automatically be put in last place as least significant or least contributing resonance structure. And then the last one is to compare the difference in electronegativities. If we see here, this oxygen molecule has a negative charge, while this in this one, the carbon is bearing the negative charge. And we know that oxygen is more electronegative than carbon. So the oxygen would bear the negative charge better. So this would be more significant than this one. In the case of positive charges, it's the opposite. The less electronegative the element is, the better it stabilizes the positive charge. So in this case, the oxygen has a positive charge and the nitrogen has a positive charge on this. And we know that oxygen is more electronegative than nitrogen. And since this case, we're looking at the opposite, nitrogen is less electronegative, so it's going to bear this positive charge better, making this more significant. Do these make sense? All right. Let's do some resonance practice. I want you guys to order these from the most significant to the least significant. I'll do the first one with you guys. So the first rule that we always look for is if every atom has a full octet, we can see that these two have a full octet on every atom. However, this one, we have a carbocation here, so that means it's not a full octet. So we can obviously put this in third place, or the least significant. And then to compare these last two, we can see that this last structure here has more formal charges than the structure here. So because of that, we can make this the second most contributing and this the first most. Does my reasoning make sense? Yeah, so just use those 3 rules that I told you guys, and you should be able to rank them from most significant to least significant. Try the next 2. Thumbs up if you guys got the answer. Seems like a lot of you guys, so I'm going to move on. All right, so in this second example, we see that everything has a full octet. By the way, to tell if anything has a missing octet, it's basically if you have a carbocation that's going to be not a full octet. Carbocation is the biggest indicator that it's not a full octet. So in this one, we see that all of them also have one negative charge. So we can't use that to determine which one's more significant. But these charges are all on different atoms. We can see here the first one, it's on a nitrogen, negative. This negative charge is also on a carbon here, and the negative charge is on a oxygen in this one. And to determine which one's more significant, we're going to use the argument of electronegativity. But we know that oxygen is more electronegative, so it can bear the negative charge better. So we would bring this one, this 2, and this 3 because nitrogen bears the negative charge better than carbon. Last one. Like I said, if you have a carbocation, that's a big indicator that it's not a full octet. And we see that in this first 2 structures, we have a carbocation right here and a terminal carbocation right here. So we can automatically put this one right here as number 1, most contributing. And then to rank these last 2, we can see that this positive charge on the first molecule is internal. It's an internal carbocation, and it can do more resonance structures because we can take a lone pair from the oxygen and do like this, or we can take this double bond and do another resonance structure. So this has 2 potential resonance structures, while on this last one, we only have 1 other potential resonance structure, which makes this, the last one, more insignificant. So because of that, we'd rank it like this. Does that make sense to everybody? All right. All right, we've finished resonance. We're going to do acid-base chemistry now. All right, acid bases, let's start simple. We're going to use the Bronsted-Lowry acid bases and the Lewis acid base definition. Bronsted-Lowry acid, saying it's donating protons, which in this case is going to be a hydrogen atom. Bronsted-Lowry base, it's going to accept a proton. Lewis acid is going to use electrons as argument. It's going to accept electrons, while Lewis bases donate electrons. So if we see this example on the bottom, we can use either definition to justify whether it's a base or an acid. So if we see this first molecule here, this is a Bronsted base because it's accepting a proton. We see that this negative charge is going, more so this lone pair is grabbing this hydrogen on this ethanol group, and it's gaining a hydrogen atom in the product. So it's going to be a Bronsted base. If we use the Lewis base definition, we can see that this lone pair here is being donated to this hydrogen right here, right? And now this lone pair that was initially localized on this nitrogen atom is being shared in this bond between the nitrogen and hydrogen. So it's donating electrons, meaning it's a Lewis base. You can use this same logic with this ethanol here and justify it as an acid, but for the sake of time, I'll skip this for now. All right, acid bases, another key component in acid-base chemistry is your ability to know what pK values are. pK values basically measure how good the molecule is at being an acid. And to interpret this value, if the pK value is lower, that means it's going to be a strong acid, or on the flip side, the conjugate base is going to be more weak. And if it is a higher pK, it's going to be a weak acid or a stronger base. So if we see this table on the right here, which I grabbed directly from your guys' textbook, we see that the pK here is -9. So this makes this the sulfuric acid the most strongest acid. On the other end, if we have a high pK, it's going to be a really weak acid, but a strong base. All right. And this is important later on because it's going to help you determine the shift in equilibrium, whether it favors the products or the reactants. All right, this slide is a jumble of words, but basically what it's saying is when you're comparing, it's basically saying the more stable a molecule is conjugate base, the more acidic the molecule. So the stronger an acid, the more it's likely to dissociate or donate its hydrogen atom, right? And once it donates that hydrogen atom, it's going to bear a negative charge. So for example, if we take ethanol here and we deprotonate it, we're going to get this charged molecule right here, right? And it's saying that the more stable the conjugate base, which is this deprotonated form, the more acidic that molecule is. So how do we judge which conjugate base is more stable than the other? That's where ARIO comes in. ARIO, A-R-I-O. Each letter stands for something. The A in ARIO stands for atom. The R stands for resonance. The I stands for induction. And the O stands for orbital, or more familiarly, hybridization. So let's start up with A. The atom, it's saying that for the atom, if the conjugate base, the charge is on a more bigger molecule, a bigger atom, that means it's able to bear that negative charge better. So it's going to be more stable. But you only compare the size column. So for example, if you had a negative charge on a oxygen versus a negative charge on a sulfur, if we look at the periodic table, sulfur is bigger than oxygen, right? And it's in the same column. So we compare the size differences, and since sulfur is bigger, it's better able to stabilize this negative charge, making this more stable conjugate base, meaning a stronger acid. If it's not in the same column, but in the same row, for example, like nitrogen and oxygen, in this case, we're going to compare the electronegativity differences. We know that oxygen is more electronegative than nitrogen, so it can bear the negative charge better, meaning that it's going to be a more stable conjugate base. So in this case, the oxygen bearing the negative charge would be a stronger acid. In the case of R now, let's move on. R stands for resonance, and this is basically saying whichever conjugate base can do more resonance and has resonance is more stable than the other, which is why we learned resonance before we did acid-base chemistry. The I in ARIO stands for induction, and this is basically saying that if you have a electron withdrawing group close to the negative charge where it is, then it can better stabilize that negative charge because the negative charge can sort of dissipate better than if there wasn't an electron withdrawing group. Last one, we got orbital or hybridization. This is basically saying that if you have an atom that has a greater S character, that means it's going to be more stable. So the trend follows. SP is greater than SP2, then greater than SP3, because SP has the greatest number, the greatest percentage of S character. Because SP has 50% S character and 50% P character, while SP2 has 33% S character and 33%, 66% P character. While SP3, it's split in four, so the S character would be 25% and the P would be 75%. It has the least amount of S character, meaning the most unstable. Any questions on what ARIO acronym stands for? Do my explanations make sense? All right. Okay. We just went over this, so electronegativity and the size of atoms, that's A. Resonance, inductive effect, and hybridization, or O, orbitals. So let's do some practice problems. We're going to rank these from most acidic to least acidic. And to do that, you're just going to deprotonate these molecules and compare their conjugate bases. So let's do the first example together, actually. Where's the answer? We see that if we deprotonate A, we're going to get a negative charge on the oxygen. Negative charge on this oxygen. Negative charge on this oxygen. So we can see that the negative charge is all on the same atom. So we can go on to the next acronym in REO, the resonance. We see that structure A can't do any resonance. There's no resonance patterns we can do. So this would automatically be put in third place for the least stable, the least acidic. And then comparing these two can do resonance because you have a conjugated pi system right here, which was one of our resonance patterns. So these both have the same resonance patterns. And then we're going to move on to I in REO, which is an inductive effect. And we see that in molecule B, we have this CF3 and this fluorine. Let me draw it differently. Has an inductive effect such that this negative charge right here is stabilized by the fluorine atoms. Whereas in this last one, this last structure, there isn't any fluorine atoms to mitigate the negative charge. So that makes this molecule B more stable than molecule C. And the more stable it is, the more acidic it is. So since B is the most stable conjugate base, it's going to be the most acidic. And then we're going to have C and then A. That's how you rank it from most acidic to least acidic. Does my walkthrough make sense? Any questions regarding anything? Yeah.
Is B more negative? Is that why it's?
Electronegativity, that's part of the acronym A. And we established that the negative charge is all on the oxygen molecule, so we can't really use the electronegativity argument to justify whether one is more stable than the other. So then we moved on to resonance, and we saw that A can't do resonance. So now we're comparing B and C, and B and C, the only difference is that B has a electron withdrawing group, which is right here, which makes it more stable. Any other questions? All right, I want you guys to do the next two then. Let's do these examples together. If we look at the second problem, show all of them in the deprotonated form. So we get oxygen with a negative charge, carbonyl group, I, and it's the same case for the rest, just with different inductive groups. So in the first one, we see that all the structures are the same except for these groups right here, iodine, bromine, and fluorine. And since they're all in the same column, we're going to compare the atomic sizes. And we see that iodine is the furthest down, meaning it has the most electrons, making it the most biggest. And since it's the biggest atom, it can better stabilize that negative charge, making a more stable conjugate base, making it a more acidic molecule. So that would make it A, then B, right? Yeah, then B, then C. Any questions? I use the argument of, yeah.
So that's only if it's in the same column of the overall size.
Yeah, you only compare size if it's not in the same column, but in the same row. Usually. You could, in that case, I would compare the electronegativity, right?
Yeah, probably electronegativity,
Yeah.
but check with your professor and see what they would prefer. This definition that we pulled though is straight from your textbook.
So yeah, let's look at the next one. If we deprotonate this, we're going to get a negative charge on here. God. Negative charge on here. And negative charge on here. So we can't use the argument of atom, the atomic size or the electronegativity difference to justify which one's more contributing. But we can use the argument of resonance to say that structure A is going to be the most acidic because we see that we can do a allylic lone pair. And you get the structure. Fuck. And you can do another resonance structure, but I won't show it. So yeah, A is the only one that can do resonance, so that would automatically make A the most significant. For B and C, we can't use the argument of induction as well because there's no electron withdrawing group. So we move on to O, which is orbital or hybridization. And we see that B, this negative charge is on a sp3 carbon, and this one, the negative charge is on sp2. And we said that whichever one has the more S character is going to be more stable, right? And sp2 has more S character than sp3. So that makes C more stable than B. So we'd rank this A, C, B. Yeah.
What is this? So this one has a hydrogen also. Right, that make it 4 points. There's another hydrogen. Yeah.
It's assumed that you know where the hydrogen is with skeletal structures.
If it didn't have that hydrogen, it would probably have a formal charge on it.
Yeah. Do these make sense? All right. Second, practice with acid-base chemistry. You're going to identify whether it's going to be a Lewis acid or a Lewis base for these molecules, and then show the arrow pushing mechanism. So for this, I'll do the first one together. Hold up. We see that oxygen has a lone pair. Aluminum does not because it's forming 3 bonds already. And since this oxygen is donating, electron donating, and we can go back to C, electron donating is a Lewis base. So this would be a Lewis base. If we want to use the other definition as well, we could have. We can see that, actually we can't use Bronsted base because it's not accepting any hydrogens. Sorry about that. So that means this would be a Lewis acid. And that would be the proper arrow pushing mechanism. You start from a source of electrons and attach it to the aluminum. And you get something like this. That would be a positive charge on the oxygen and a negative charge on the aluminum. So that's what I want you guys to do for the second one. Let's do this one. Nitrogen here, it's going to have a lone pair because it's a 0 formal charge, and nitrogen is a 0 formal charge if it has 3 bonds and 1 lone pair. So we take this lone pair, source of electrons, and then bring it and bond it to this boron, and then we'll get something like this. And we get a negative charge here and a positive charge on the nitrogen. Any questions? All right. So that covered acid-base chemistry. We're going to move on to nomenclature, but for the sake of time, nomenclature is just a set of rules. So that's all you need to follow. And we made a nomenclature guide specifically for this, listing all the steps in the proper order. So just scan the QR code and you'll get instructions.
Secret wizard scrolls of nomenclature right here.
What
For free.
Is this already up on the website? Yes.
Yeah. These blending slides will be posted on our website if you want to write that.
Yes.
And if you want to go back and see how we've solved through these problems, we post these recordings on YouTube as well. We have a YouTube channel for this. All right. Anyone still scanning? All right. Okay, let's move on then. Let's jump straight into some practice problems. So 3-iodo-6-methyl octane. First thing you do, look at the parent chain. We got an octane, meaning 8. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 carbons. That's going to be our parent chain. And then we have a 3-iodo. So that means if we number it from here, we can give this an iodine to make it 3-iodo. And then 6 would be 4, 5, 6 right here. And that's it. Simple as that. When you're given the name and you have to draw the structure, it's much more simpler than being given the structure and trying to name it, which is what we're going to do on the next one. All right. So the next one, we can see that we have a cyclic structure right here. So that's going to be our parent chain. It's only going to be the parent chain if the cyclic structure has more carbons than the main parent chain. So, like for example, we have a 4-carbon chain here, but it's not more than, it doesn't have more carbons than the cyclobutane right here. So we're going to use the cyclobutane as our main parent chain. So you can put cyclobutane at the end. Actually, this may be quite long, so I'll just write it out here. That's going to be our parent chain. And then to start numbering, we would put this as number 1 substituent because it's the biggest. And it has a bromine. So we number this 1, 2, 3, 4. And that way we can start naming these substituents. So let's name this one actually. This one is going to be, it's comprised of 1, 2, 3 carbons. So it's going to be a propyl, but it has a bromine group on the second carbon. So it's going to be a 2-bromo propyl substituent. And that's going to be on carbon 1. And to indicate that, write a 1 in front. Next substituent we see is on carbon 2. And we see that this is one of the substituents that you guys have to memorize. This is called a sec-butyl. And it's called sec-butyl because we have 1, 2, 3, 4. So it's a butyl group. And then sec. And this is on carbon 2. So write 2 in front, hyphenate it. And then on our third carbon, we have an iodine group, which you can just say 3-iodo. Okay, now that we've done that, we're going to alphabetize this when we write it. We see that we have a bromopropyl, sec-butyl, and a 3-iodo. Of these 3, bromo and butyl come before iodo. So we're going to write those 2 first. And between bromo and butyl, R comes before U. So we're going to write this substituent first. 1, 2, bromo, propyl. And then the next one is going to be this sec-butyl. 2, sec-butyl. Damn, I'm running out of space. And then we got the 3-iodo. 3-iodo. And we just connect all this. And then cyclobutane, your parent chain. Does my thought process make sense? Any questions regarding how we started numbering the parent chain or which substituent took more priority over another or anything like that? All right. Let's try these. Try naming these. For the sake of time, we're gonna roll with it. Let's see. I'm only gonna do these two examples here. The last two. So we see that we have a cyclohexane ring. Or we can use this 1, 2, 3, 4, 5, 6, 7, 8 carbon chain, which would be an octane. And we use the straight hydrocarbon chain that has 8 because it's more carbons. That's the biggest parent chain you can have. So the cyclohexane would actually be a substituent. And to change the cyclohexane into a substituent, you just put YL at the end. So this would be a cyclohexyl. All right. So to name this, write the parent chain and then identify all the substituents. We got a bromine on the first carbon, so that's 1 bromo. We got a methyl on the second carbon right here, so that'd be a 2 methyl. Oops. And then we got an ethyl group on the third carbon, so 3 ethyl. And then on the 8th carbon at the very end, we have a cyclohexyl group, so 8 cyclohexyl. All right. So we named all our substituents. We identified the parent chain. We know the correct numbering to give us the most substituent as possible. So now we're just going to combine everything together. So like I said, octane is our parent chain. And then we're going to alphabetize this. Bromine starts with a B, first letter of the alphabet, closer to the first letter of the alphabet. So we're going to put bromine first. And then cyclohexyl will be the next one since it's a C. And then the next closest would be an ethyl, so 3 ethyl. And then a 2 methyl. Octane. It's a long ass name, but that's the answer. All right. Next one, we're given the name, draw the structure. Did you have a question?
Yeah, so you said you have to include the 8 cyclohexyl.
Mm-hmm.
Is that, where was that? Is that the,
Yeah, this is the hexagon right here.
how do you get the 8?
The 8 is to indicate where on the parent chain it is. So if we count the parent chain,
Oh, you started it.
yeah, 3, 4, 5, 6, 7, 8. And since it's on the 8th carbon, it's 8 cyclohexyl. All right. This one, trimethylheptane. Heptane is going to be a 7 carbon chain. So draw 7 carbons. 1, 2, 3, 4, 5, 6, 7. 1 bromo, 6 chloro, 1, 2, 3, 4, 5, 6. 2, 2, 5 trimethyl. So there's going to be 2 methyl groups here. 2, 3, 4, 5, and a methyl group here. Simple enough, right? All right, that's nomenclature. Yeah, no. We're gonna skip for the sake of time. Okay, we got bicyclic nomenclature now. This one's probably a lot harder, but if you look at our nomenclature guide, you'll see. So to do this, you count from the bridgehead carbons, either one of these, and we're gonna start from this one right here because if we get this carbon 1, we'd have a substituent right on carbon 1, as if it was right here, the carbon substituent would be on the second one. So we're gonna name starting from right here. Number this 1, and then go around the bigger cycle ring. 2, 3, 4, 5, 6, 7, 8. The bridgehead carbon also counts. So then we'd have a bicyclooctane. And we got to put in brackets the numbers. And the numbers indicate the bigger bridge. You count the number of carbons on the bigger bridge, which is right here. We have 1, 2, 3 on the bigger bridge. And on the smaller bridge, we got 1, 2. And then on the bridge head, we got 1, right? So list those numbers in order. 3.2.1 octane. And then you put in the substituents now. And we have a methyl on carbon 1. So 1 methyl. And then on carbon 4, we got an ethyl group right here. 4 ethyl, bicycle 3,2,1 octane. All right. All right. It's going to be the similar structure, similar idea for the rest of these. So do these at your own time. We post the answer keys to these as well. So let's move on. We got Newman projections now. I'm pretty sure this is relatively new to you guys. Probably started learning this last week. Newman projections is basically how you project a 2D structure, a 2D skeletal structure into a 3D object. So to interpret a Newman projection, we see the central carbon here, the front carbon, and then the back carbon is indicated by the circle here. So it means the carbon's right in the back. If you're looking at the molecule straight forward, the carbon in the front is this dot that I pointed at in the red arrow. And this circle in the back is the back carbon. All right. And then you can add the substituents, which you can have 3 bonds. So you're going to have 3 substituents like this. All right. So to show you guys, it's asking us to draw the Newman projection from the skeletal structure, right? And we're looking through this angle. Think of this as an eye looking through from this angle. If we're looking straight forward, we can say that this ethyl group is going to go straight down because it's in the plane. But this tert butyl group is going to be towards our right if we're looking straight down. So this tert butyl group would be like this. And since this methyl group is on a wedge, it'd be like right here. And then since we did that, let me color code this. This carbon right here is this carbon. And we're looking straight down. And then let me color code again. This carbon right here, the back carbon, we're going to draw a circle to indicate that. And then we're going to draw the substituents. So in this case, the methyl group is out the plane. So it'd be right here. And then even though you don't see it, this carbon actually has a hydrogen on a dashed line. So we'd write it like this and then put an H to indicate it's a hydrogen. And then this isopropyl group here would be in the plane. So you'd structure like this. Yeah. One more time, sorry. This isopropyl is because so to indicate whether it's going to be up or down in the Newman projection, if it doesn't have a wedge or a dash, that means it's either going to be written straight down or straight up. That's why since this isopropyl is not a wedge or a dash at all, we can write this to go straight up like this. And then this ethyl group is also in the plane without any wedges or dashes, so we can write this straight down. And this hydrogen, you asked, if this methyl group is coming out in front of us, that means the hidden hydrogen would be going back, right? So, and since this tert butyl group right here is also going back, that means this hydrogen would also be in the same direction. Since this tert butyl is towards the right, this hydrogen on the dash would also be on the right. Does that make sense? Yeah, these honestly is just about practicing. You got to do a crap ton of practice with this to fully able to understand. So that's the original structure, and this is called a staggered conformation because it's all spread out and it's forming 60-degree angles. And then we can draw an eclipse version in which these bonds are directly on top of each other. And to show that, we can either rotate the back carbon or the front carbon. I'm going to rotate the back carbon for simplicity. So we can draw the front carbon again. And then the back carbon we rotated like this. So to show that, this isopropyl will now be behind this tert butyl like this. This hydrogen rotated now, and it's behind this ethyl group. And this methyl group is behind the methyl group like this. And that's how you show that the back carbon and the front carbons are totally eclipsed, meaning the substituents are like right in front of each other. All right. And this would lead to the highest energy conformation because the two biggest groups we have, this tert butyl and this isopropyl, since these are so large, when you actually rotate them, they're going to come into contact with each other, and molecules do not like that because that's called steric hindrance, and that's not energetically favorable. That's why when we rotate it like this and they're directly on top of each other and they're making contact, this is called the highest energy conformation. All right. And then on the contrary, the lowest would be then if the two largest groups were the furthest away, which in this case would be 180 degrees. So we can rotate it again. And rotate the back carbon. And now this isopropyl is going to be 180 degrees from this tert butyl. And if this rotated towards there, then the hydrogen would be right here, and the methyl group would be right here. And that would be this would also be a staggered conformation, by the way. And this would be the lowest energy conformation. All right? Does that make sense?
So would we like take which one is the most favorable?
What do you mean favorable?
Like
Oh, like
like
I guess the most favorable would be when it's the lowest energy conformation. So this would be the most favorable. Mhm. But we typically only use that term for resonance if it's more favorable than the other.
we wouldn't like
Not really. You don't break these.
They might ask you to rank it from like lowest energy to highest energy.
Mm-hmm.
So
That's
you
true.
Know this.
For the sake of time as well, we're gonna skip the next one. You guys can do this on your own time. The answer key is posted. More practice. The same story. Okay, so the two types of questions that Jessica can ask with Newman projections is going from a skeletal structure to a Newman projection, and the other way around as well, where you go from a Newman projection to a skeletal structure, which is what this question is tackling. So we see this Newman projection here. We can indicate this front carbon with blue for simplicity, this back carbon with green. So to draw a skeletal structure, we can show that the green and the blue are forming a bond. All right. And we see that on the blue carbon, we have two methyl groups. So we can draw two methyl groups like this. And then since this ethyl group is within the plane, we can draw something like this to show it. And then the back carbon, this green highlighted part, we see that it has two hydrogens coming off, and you don't show hydrogens when you're drawing skeletal structures, so you omit that. But you show this propyl group right here. And since it's going straight down, it's going to be in the plane. 1, 2, 3. That's a horrible structure. 1, 2, 3. And that's how you would draw this molecule. And then from here, you can, it says to name the IUPAC name. You can just name it because you guys know how to do that. All right. The core point here is to be able to go from a Newman to a 2D structure. It's going to be the same story for the next one as well. All right. All right. Last one. We got chair conformers. I heard you guys voted to have this on the exam, which is a good thing because the next few chapters are going to be more difficult and you don't want to cram all this in one single exam. So good on you guys. Chair conformations is kind of the same story with Newman projections in the sense that you're taking a 2D structure and converting it into a 3D structure so that you're able to see the bonds. And usually when you do chair structures, you're going to be working with cyclohexanes. In cyclohexanes, we have something like this, right? This is a cyclohexane, and each carbon here would have two hydrogens. And when we convert this into a 3D structure, we get something like this. And you can count because we have the same amount of carbons. 1, 2, 3, 4, 5, 6, right? And to show the hydrogens, these hydrogens are going to be placed in a specific conformation such that the hydrogens can either be up or they can be down like this. It's directly up and this is directly down. And it can be up or down, but it can also be equatorial or axial. Axial means that it's going to be just like straight up, and equatorial means it's slightly bent towards the downside or the upside. So for example, if we draw all the hydrogen in, we can see that, for example, this hydrogen is straight up, so it's an axial hydrogen and it's up. For this one, we see that it's slightly bent downwards. So it's going to be going in the down direction, but it's not completely down like this one. This one is completely down, but this one is down at an angle. So this would be an equatorial position. Similarly, this one is also up, but it's at an angle. So we make this an up equatorial. And then this one right here would be a down axial. All right. This,
So on the left side is where with the light on the right side is where with the light on.
as a 3D structure, yes. It technically still isn't 3D since it's on a flat surface, but that's how you'd see it, basically.
Right.
All right. So first practice, same thing I did. I want you guys to identify whether A, B, C, or D are down, up, and axial or equatorial. So you're going to use two words to describe these positions. All right. Actually, let's just go over this together. Anyone got an answer for A? Yeah. It's in the up direction and it's straight up, not at an angle. So up up axial. What about B, guys? Yep. Seems you guys got this. What about C? Down axial, yep. What about D? Yep. All right. Next concept with chairs. This is important. He's probably gonna ask you guys something along the lines of doing a chair flip. Chair flip, it's pretty simple, but it's hard to imagine in your head doing a chair flip. But the easiest way to draw a chair flip from a given chair conformation is to basically any substituent that you had that was up and axial is going to become an up and equatorial. Vice versa, if it was down and equatorial, it's going to be a down axial. If it was up equatorial, it's going to become up axial. So whatever it was, the direction stays the same, but it's going to change from an axial position to an equatorial or an equatorial position to an axial. All right. So I'll show you guys an example for real quick. So if we do a chair flip here, we're going to change this structure. Oops. God, this is a terrible chair.
You got it.
Yeah, chairs are kind of hard to draw, but it comes with practice. So anything that was equatorial, anything that was equatorial, it's going to become axial. Anything that was axial will become equatorial. So for instance, this ethyl group here, it's axial, right? So in this case, since it's up axial, it'll become up equatorial. So you can write this, and now this ethyl group is equatorial. I'll number these carbons for you guys so it's easier. I mean, yeah, I'm not taking into account the groups here per se. I'm just more so numbering this for the sake of simplicity so that you guys can see how it changes from axial to equatorial. But yes, you would probably do this. But I'm just going to do this for simplicity. 1, 2, 3, 4, 5, 6. So on carbon 1, this ethyl group it transformed from an axial position to an equatorial. So this is now equatorial up. If we look on carbon 3, we had this methyl group. So on carbon 3, since it was up axial, it'll be an up equatorial now. And then on carbon 4, we had a equatorial hydroxyl group. So now it'd be up axial like this. All right. So yeah, you just flip everything around basically. Anything that was axial, equatorial. Anything that was equatorial, it's axial. The direction stays the same.
Just gonna go clockwise 1, then it's axial and equatorial. It's axial.
Yep.
So over there, that shows kind of how it looks.
Does that make sense?
Yeah. Yeah.
All right. All right. This next part is talking about the energy. So typically, if you have a chair conformation and if you compare these two, one of these, both of them are in an axial position. But this one, they're both in an equatorial position. And equatorial positions, they're at an angle such that the two substituents are further apart and they can't make much contact with each other, meaning less steric hindrance. So that means it's more energetically favorable. So that means this is more stable. So general rule, just follow this. If it's equatorial, then it's more stable. If it's axial, it's less stable because of steric hindrance. Is that all? Okay. I'll do one of these with you guys, and then you guys are free to leave. Sorry for holding you guys for so long, but let's see. Chair structure. If you guys are wondering how to draw chairs, here's a quick way to do it. I draw 2 parallel lines like this, and then 2 parallel lines like this, and then 2 parallel lines like this. And that's a good way to draw a chair.
Do it again.
Yeah, I'll do it again. So 2 parallel lines, and then another 2 parallel lines, and then another 2 parallel lines. So you're essentially just drawing 3 sets of parallel lines, and that's it. All right. Okay, sorry. Let me be quick. So we see on this carbon, we have an up arrow because it's on a dash. So it's going to be up. On the next carbon, we have an up as well. So this would be up. And then on carbon 4, 3, 4, it's down. So it'd be like this. So that's one of your chair structures. And then the other chair structure would basically be a chair flip. So just draw this as a chair flip. So now this up axial becomes an up equatorial. This up axial, this up equatorial becomes an up axial. And then this down axial becomes a down equatorial, like this. Any questions? No? All right. It's the same case for this one as well, so try it out yourselves. Oh, and by the way, we posted a practice exam in a similar style to Jeski's on our website. So you can time yourself and see how you do on those. And yeah. That's all of it. And I hope, yeah. If you guys can, fill out this QR code and tell us how we did.